Hi, this is Anna, and this video is about converting a C loop into a Risc-V assembly. So we will start with a simple C loop and then see how we can manage our chars on the stack in Risc-V. Let's create our C program first, and we call it loop underscore C, and extension would be C, and we can open it up in our Visual Studio Code now. Okay, so what we want to do here is we want to include uni std header first, so we can have an access to the right system call. All right, so let's define our main. We want to write our for loop. And for example, we want to loop from value 5 up until 0. So let's initialize our value I to 5. And then we loop until I more than 0. And then we want to decrement I on each iteration. So what we want to do inside of the loop is we want to convert each integer into our char variable. And we can do that by adding, and here Copilot is helping me, magic ASCII 0 to variable I. And now we can use a write system call to print our character, and a write system call has several parameters. So the first one would be one for a standard output, which is a terminal. Then we want to give the address of our char, and the last would be the size that we want to print is, and because we're printing just a character, it's only 1 byte. And what we want to do now is just return 0. And our C program is ready to compile. Okay, so we just say GCC and then the name of the program, which is loop underscore CC, and then O, and the output would be loop underscore C. Oh, that's okay. So here's an extra parentheses. You see, that's why people hate Copilot. Let's try to compile again. All right, so now we can run our program and say loop underscore C. And here we have our values 5, 4, 3, 2, and 1. So now we are ready to convert our C program into a Risc-V program. And for that, we're gonna have to call for help. Let's just say moon prism power, like the tech magic happen. Woo! Hi there, it's Sailor Moon here, your Risc-V tech specialist. Okay, so let's create our Risc-V program by saying touch and then the name. We can say loop underscore s dot s, and we can open it in our Visual Studio Code. All right, so now we have our Risc-V program and the C side by side. Let's start by writing our first section, and this would be our text section. Risc-V is divided into sections. So our first text section is a section that contains the executable instructions. Then there is a data section for initialize global variables. And then there is also the beqz section that is used for initialize data. And in the previous video, we used the data section to store our variables, which means that the data was fixed in the program's binary. But in this video, we're going to be learning about stack. So unlike data section, the stack is created at the runtime and is used for temporary data that only lives a short while the program runs. Okay, now that we have our text section defined, let's define start as a global to tell a linker and assembler where the program should start executing. So in our C program, we use in two system calls. We use in a write system call right here, and we use in the exit system call. We also use in a file descriptor one. So we can save std out, which is our file descriptor one. Then we also want to save the system call numbers associated with system call write and system call exit. Okay, so let's look at the Risc-V Linux syscall table to find the decimals associated with the system call numbers that we need to use. So let's look up write, and write is associated with 64, and let's look up exit at the same time, and exit is 93. So we can save those in the variables, and let's say write syscall is 64, and then the exit syscall is 93. And Copilot is doing a great job this time. So now we have our special number saved. Next time we open a program, let's say a year or 10 years from now, we will know exactly what these numbers mean. Let's look at our for loop. So our for loop has three parts. The first part is initialization, then we have a condition, and we have an update. So what we want to is we want to load our first value 5 into a register. Let's check out the registers that we want to use, and here I have a cheat sheet for the registers, and we are not trying to save anything, so we can use this temporary registers T0 through T2 and T3 through T6, which is the temporary registers. And we want to just load this immediate value. So we need to look at the Risc-V assembler cheat sheet to find an instruction for immediate value. Okay, so this is to add immediate value, but we want to load immediate value here. So we have li instruction that loads immediate value into the register. Okay, let's go ahead and use this instruction and just say li T0, which is the first temporary register. We can load 5 in it to initialize our loop counter to 5. Okay, and now we are ready to start our loop. All right, so what we want to do now is we want to look at this line where we converting our decimal to ASCII, which is just adding 0 to a value in our now T0 register, right? So we want to use next instruction that actually we just looked at. We can use this add die instruction to add an immediate value to a register and store it in another register, the destination register. So let's use our add die instruction, and we want to store our value in the next temporary register, and we want to add the value from T0 and the magic number 0 from ASCII. So now we initialized our counter, we converted it to ASCII, and we're ready to use our write system call. But before we can use the write system call, we want to store our temporary values somewhere. Okay, so imagine this is our stack, and stack actually is not empty, it already has some data in it. So this slots would be containing the data, and it also has some free slots in it. So stack actually grows downward. So a stack pointer is going to be pointing to the top of the stack right here. So this is our stack pointer. And we want to go through values 5, 4, 3, 2, and 1, right? So what we want to do first is we want to take this decimals, right? And we already done it. We converted them to char characters, and char characters are only 1 byte each. So we want to reserve a space for this character, and we can reserve a space by moving our stack pointer downward by decrementing it by 1. So now we can move the stack pointer to the next free slot. All right, so now our stack pointer moves to this slot, and we want to take our decimal value 5 and move it into our free space, right? So now we can store 5 in here. Okay, so now the value 5 is at the top of the stack. So what we want to do is we want to use a write system call. A write system call knows exactly where the stack pointer points with the offset of 0. So the next step after the write system call is executed would be to restore our stack pointer to where it was before by adding 1 byte, because we're working with chars, and moving the stack pointer back. So now it's pointing right here. Actually, we still have our value 5 on the stack, but we don't really care, because on the next iteration, when we are working with 4, we're just gonna go and override it here. So now that we understand the concept, let's go ahead and try to implement it in our Risc-V. Okay, so let's look at the registers. See, we have SP is a stack pointer, which is a special register, and this is the register we're going to be using to work with our stack pointer. And now we want to look at the instructions. And the first instruction would be just an add instruction, because we're going to be adding an immediate value of -1 to our stack pointer. So let's go ahead and use this instruction. So we just say die and then sp and -1, just because of chars. But if it was integers, it wouldn't be -1, it could be -4, for example. The next step is to store byte at the top of the stack, and let's look at the next instruction we can use. It's the store a byte. And here we have load and store instructions, and we want to use SB, which is a store a byte. Okay, and here we want to use T1 as our source register that holds this ASCII character value. Okay, so this part here is the memory address we are storing to, and it's called base plus the offset addressing, and the base is SP, the current value of the stack pointer, and the offset is 0 because we aren't shifting, we store exactly at the address stack pointer points to. Okay, so let's go ahead and use this instruction. We just say SB, and then we want to use T1 and the offset of 0 with our stack pointer. Now we have our stack pointer situated, we can actually use the write system call next. So we want to load 1, which is a standard output first. Then we want to point to the address of our stack, and then indicate the number of bytes we want to be printing. And we also need to load our write system call into a register. Let's look at the registers we want to use. We can't use the temporary registers anymore. We want to use the function arguments instead. So these are A0 through A1, and then there are also A2 through A7. A7 is a special register for the system calls. Okay, so we already used li instruction to store an immediate value in a register, and we can use the register A0, the first register, to store std out, which is 1. And now we want to move our stack pointer to the register, the next register A1. Let's look at the instructions. We want to copy the register, and here the copy register is used with this mv miscellaneous instruction, and we use mv to move our register, which is a stack pointer in our case, into this destination register, which is going to be A1. So let's use this instruction and just say mv A1, and we want to move our stack pointer in there. And the last parameter is the number of bytes, so we can use li again with the register A2 and put just 1 in there. All right, and I almost forgot, but here Copilot is helping me. We should not forget about the write system call itself. So let's load our write system call into this A7, and we are ready to transfer control to the OS. And for that, we want to use another instruction. And if you saw, Copilot was helping me. So this is equal environmental call that we can use to transfer the control and execute the system call. So let's use this instruction equal. And remember what we did after executing the right system call is we actually had to clean up the stack and move the stack pointer back to where it was before by incrementing it by 1. Okay, and now we can decrement our loop counter by 1 as well. And we use this ADA instruction again, and the value where we stored our variable I was T0. So we just need to decrement T0 by 1. And this was our just first iteration. What we want to do now is we want to go back to the top of the loop, right? So for that, we want to use a jump instruction. And the jump instruction is just just jump instruction. And we just say jump and use it with immediate value. Our immediate value is actually the start of our loop. Okay, so now we want to go back to the start of the loop, and we want to look at this condition when I more than 0. And for that, we need to use another instruction, branch if equals to 0. Let me see. Here are the branch instructions, and here, oh, it's staring right at me. It's branch if equals to 0, beqz. Easy to memorize, so we just say beqz. If our T0 is equal to 0, we want to go to the end of our loop, and we can just define our end in here. So if we look at our C program here, we return in 0. So what we want to do in our Risc-V is we want to load our 0 into A0. And we next want to load our exit system call 93 into a register A7. And we then can use a equal to transfer control to the OS. And if we look at all our instructions here, I see a minor arrow. So here I forgot a comma, and this actually should be comma as well. So now that everything looks good, we are ready to assemble our program. To do that, we want to say Risc-V and then 64 unknown elf and as dash O. The output we want to give is loop underscore s dot O, and the name of the program was loop underscore s dot s. So this will assemble our S program into object O, but it doesn't link it. So the next instruction we want to do is we want to link this object to an executable. Let me just change this really quick. And we are ready to run our program. What did we call it? Loop underscore S. And here we have all our values listed. And that's it. So this is how a simple C loop turns into a Risc-V assembly. Don't forget to like and subscribe, and leave me a comment if you want me to cover other instructions. There are a lot of suggestions that I got already, and I try to implement all of them in this video. If you have more ideas for me and more optimization techniques, please do share. I do take everything in consideration and try to give you the best content possible. If you like my videos, consider becoming a paid member on Patreon or buy me a coffee to fuel my enthusiasm. I need to keep a level of coffee really high. Anyways, see you next video. Bye-bye.